All right, I just want to do one more example for this molecule. And how many unique hydrogen environments are there? Well, I hope you recognize that down here we have a methyl group. So this, let's call environment 1, and it's going to be 3H. Next to it, we have 2 hydrogens on this spot. So this will be location 2 in the molecule, and that should integrate for 2H. Again, there are 2 hydrogens in that environment. Moving on to this location, again, I hope you see that there are 2 hydrogens here, and this is now the 3rd location, unique location in the molecule, also 2H. And now we arrive at this spot right here that has a single hydrogen lurking. And so that spot right there is going to be the 4th unique environment, and it's going to integrate for 1H. And then lastly, I hope you recognize that the 2 methyls are in fact related to each other by symmetry, according to that plane right there. And so they are environment 5, but you would expect 6H for them. Now, the last thing I want to point out here is that you can make some predictions about chemical shift, and I would invite you to do that. As you are thinking about integration, what you're inherently doing is looking at each environment in and of itself. And while you're doing that, you should at least think to yourself, what would the chemical shift be? So here we have a relatively boring methyl. I'd expect to be around 1 to maybe 1.2, so let's call it 1 part per million. These 2 hydrogens are next to an oxygen, so I would assume for them about 4 ppm. We're going to skip him for the moment and go on to this guy, who in location 4 is right next to a carbonyl. So I would expect right next to a carbonyl to be about 2 parts per million, give or take, maybe 2 to 2.5. And then finally, of course, these at the end of the chain are boring methyls again. So again, I would expect them to be around 1 part per million. So now we can return to the one I skipped over. And the reason why I skipped over him in the first place is because he's actually next to 2 things. He's next to this carbonyl, which should shift him left of where he might otherwise be by 1 to 1/2 part per million. And he's near this oxygen, which should shift him to be around 4. So I'd expect to show up anywhere in the 4 to 5 range, because NMR is mostly, but not entirely additive from a chemical shift perspective. So what do we expect for this guy? Well, for him, I would expect completely unique signals across the board. I would expect a 3H signal, a 2H signal, a 2H signal, and a 1H signal, and then a 6H signal. And I would expect these 2 to come near each other around 1, this one to show up around 4, this one to show up left of him, I'm not sure where exactly, but definitely left of him, and him to show up in between this guy and the methyls. That's what I expect. But core issue, when you go to do the integration here, you would want to make sure that you had a total of 3, 5, 7, plus another 6, 13, plus another one, 14 hydrogens total, and they need to be arranged in roughly the right amounts, and that's the value of integration. But in addition, if you have a need to assign things, then you can rely on integration and chemical shift to accomplish the assignments of a lot of molecules that look like this. If you see something that integrates for 3H, it's going to be that guy. If you see something that integrates for 6H, it has to be these. And these are ambiguous, but this one is not. Which raises the point that there are magic numbers for integration, and the magic numbers are round numbers. 1H makes sense. It's a single hydrogen in that environment. 2H makes sense. 4H makes sense. It's symmetry, probably, although it could be overlapping stuff. 3H is a magic number for integration. What it means? Methyl. Any multiple of 3H, 6H, means 2 methyls. 9H probably means 3 methyls. 12H probably means 4 methyls, all in the same environment. So any multiple of 3 is kind of a magic number. 4 is a number that I like okay because it probably means 2H in the same environment, although there could be overlapping peaks like here, which would complicate things. But still, 4H I like. 5H worries me. 5H is weird. That means we've got overlapping things that are coincidentally overlapping and they're not nice. There's no good way to end up with 5H. 6H I like, it's 2 methyls. 7H, weird. Again, has to be weird overlapping things. 8H I don't love, but because it could be a multiple of 4H, it doesn't bother me as much. 9H I love. You get the point. Odd numbers, except for 3, worry me a little bit. 3 and 9 and so on. The magic numbers for integration, though, are 3H, 6H, 9H. They mean methyls. Almost exclusively, they mean methyls. Let me put a tiny little caveat on that. If the multiplicity is nice, they definitely mean methyls. If the multiplicity is not nice, then something else is going on. But if you see 3H, 6H, 9H, 12H, something like that, think methyl first, and then look for other explanations if you have to.
So all I've done so far is paste the image that we were just looking at into the actual predicted spectrum. I don't have a sample of this on hand to take an NMR of, but MNova has a powerful prediction engine, so that's what you're looking at here. So now let me go ahead and integrate this, and if I just glance at these peaks, the peak that seems the smallest to me is this one, so I should probably integrate it first just to see if that ends up integrating for 1. Now, since I integrated it first, of course it's going to be 1, but my prediction is that all other peaks will be taller. So let's integrate this guy, which is probably going to be 3, and this guy over here should probably be 6 then, and then these guys should both be 2. Alright, so there are the actual integrals, and now, based on inspection, we can go ahead and assign several of these. So we mentioned that this is the one, both because he's small, but also because he's the most complicated looking guy. So when you go to the multiplicity video, you'll see why that is. And then this right here is a doublet worth 6, so it's clearly the green. And then here we have a triplet worth 3, this guy, and then a quartet worth 2, a complicated peak worth 2 is B, and then this guy right over here is the singlet and furthest left peak because he's between the two. Now, as it turns out, they predicted more like 3.5 rather than 4, and it turns out they predicted more like 4 rather than 4.5 or 5. Fine. So just to formally go ahead and wrap things up here, what I wanted to point out is that ahead of time we had predicted that there would be 3 methyl groups and that they would all collect around 1, and so in fact there are 9H down here and they collect around 1. We expected that 2 of them would lump together as a 6H group, and they have, and there was also going to be a 3H group. I made no predictions about which one was going to be further left, but if pressed, I probably would have leaned toward the thing closer to the oxygen. So chemical shift around 1 to 1.5 makes sense to me. Again, we had 2 groups that we expected to be around 4, and I would have predicted that the one between the carbonyl and the oxygen would have been further left, and that turns out to make sense as well. And then, of course, we have the 1H group in the entire molecule, which is all by himself. Now, I would have predicted him near the carbonyl to be between 2 and 2.5, and so I'm a little surprised to see him at 2.6. But again, there's a substantial amount of power to being able to do predictions based on nothing but integration and chemical shift. Now, of course, the caveat here is that this is just an NMR prediction software as opposed to the actual spectrum. But I would imagine that the actual spectrum would be rather similar to this, although perhaps the chemical shifts would be off by 1/10 or 2/10 in any direction, something like that.